Hi, this is the introductory video in a series on how to build one of these. Um, this is the Hopper 6502 single board computer, and I'm going to go through first the why and the what of it, and then later the how of it, which will include, how to get yourself a PCB, how to get a PCB manufactured in China, from my Gerber files, obviously. What tools you're going to need, and how to source the components in the most reasonable way. It's not trivial. After that, I'm going to do a series of videos on the incremental assembly and testing of the board. So you'll learn all sorts of interesting things, like how to program these CPLDs, the GEL, which is the glue logic. You program it with the same with the same EEPROM programmer, common EEPROM programmer that you would program your EEPROMs with, right? See what that looks like. One of those, yeah. Which I'll mention under tools when I talk about tools. We'll also bring this board up incrementally, so one thing at a time to make sure it all works. And that means you'll learn how to use the Hopper 6502 assembler, because we can get, Blink going without, we don't need RAM, we don't need the serial port, we just need the parallel port. We need the parallel port, the CPU, and the ROM, and we can start by getting Blink going, for example. And then we'll incrementally move up and add more and more components, culminating with the full Hopper IDE and debugger experience. All right, so in this video, let's get on with the why and the what of it. So let's start with Ben Eater, shall we? Because he's got a lot to answer for. So unless you've been living under a rock in terms of retro computing, you're very familiar with this project. So Ben, a couple of years ago, did an amazing series on building a 6502 computer on a breadboard. And it is a really good combination, a really good balance of computer science and digital electronics. So I highly recommend his series. Even if you're not going to build the board, go and watch his videos. But go further. If you haven't got a 6502 yet, buy his kit. And don't buy the serial interface, by the way. I'll just the computer kit. And if you buy the computer kit and work through his series, you can reuse those components on my board, right? You don't need the clock module, or you might for the video series, because he also runs off a crystal oscillator, CAN oscillator. So you could probably get away without the clock module and without the serial interface. Just get the kit. He also sells the EEPROM programmer, and his price for the EEPROM programmer is very similar to where I'll recommend you get it from. Anyway, like I said, Ben's got a lot to answer for. But when you get to the end of Ben's series, you're sort of left hanging with where to go next. And the where to go next for me was more about software than about hardware, more about computer science than about electronics. So my first attempt at then building my own board was really just a Ben Eater clone here. So my board was, this board here was really just his machine, his design mostly. Let's have a look at it. So I built it first on perf board, and then eventually I made my own PCB and got it in a case and all that. So you can see it's got his LCD on it, and you can't really see here, but that's a PS2 port. So this is his PS2 port over here. Those three chips and the parallel port. So the parallel port chip is driving both the LCD and the PS2 keyboard. And I actually did I bought one of these RC 2014 micro keyboard kits. Where's the picture that you'll recognize? And then I reworked it to be a PS2 keyboard. I reworked this keyboard to be a PS2 keyboard. yeah, by reprogramming the microcontroller. So been through all that. I went through the trials and tribulations of using the Western Design 6551 as the serial port. I single stepped my own clock using the Arduino Mega as a probe to debug. So you learn a lot from the stuff. Like I said, I can highly recommend his series. And then at the end of the day, I did my own thing with the serial port, and I switched to using the Motorola 6850 as my first daughter board for this design, and I never looked back. So really happy with that choice. And then moving on from there, I carried on. I developed the Hopper development environment, which is a modern semicolon and curly brace development environment here. So you can, and it's really easy to install on Windows. I'll talk about that a little later. But if I F5 here, it's going to stop that blinking light because it's loaded up the debugger. And then I can, single step in the debugger, delay, switch the LED. There we go. Switch the LED again. So yeah, so as I go past there, every time it's going to flip the LED. And I'll talk about this a bit more later. But let's just go back to the hardware again and talk about what's different about my board and why. So again, like I say, I recommend you start with at least watching Ben's videos if you haven't watched them yet. But I also recommend just building his board, just ordering his kit. Right. So I wanted to be able to program with a high-level language on these boards in a similar way to the way you would program an Arduino or any microcontroller. And what I mean by that is we don't have a self-hosted development environment on the microcontrollers. Our development environment is the enormous desktop CPU that we have, or desktop computer that we have. We use that for the development environment. And that allows us to build modern tools for these little 8-bit, these beautiful little 8-bit CPUs without having to build the development environment on the CPU. So this is not vintage computing. This is retro computing. So we really want to run our code on this chip. But we want to have, a modern development environment experience. So we want a decent editor. We want a good way of navigating projects. So let's go and have a look at that. So breaking out of the debugger here, there's our editor. It's got menus here with Visual Studio keywords. If I right-click on something, it navigates to that something. Right-click again, navigates again. I can control backspace to go back in my project. The way it knows how a project is structured is it's got this Pascal keyword of program. So there's only one program, and the program uses units, and a unit is it's a namespace. So the project is automatically structured by the hierarchy of how you've used your units, like your include files, as it were. And you can see in the top right here, your main program file is always on the right here, and you can double click on that to go back to it. And then if you have a syntax error, let's make a syntax error, pre-processing. At the bottom of the screen, let me show you that. There's an error message here, and if I double click on the error message, it'll take me to the error. It's obvious if I'm already on there, I just put the cursor somewhere else. So yeah, it jumps to the error. So not like a command line environment for developing. And Hopper is a high-level, modern semicolon and curly brace language, complete with garbage-collected memory management, but designed to run on small devices like the 6502. In addition to the Hopper programming language, I also have a toolchain for 6502 assembly development, and I also have a C compiler for the 6502 that run in this exact same environment. So when you're familiar with the one environment, you're familiar with it all. And then in terms of what do I mean by a full debugging experience, if I F5 here again to launch the debugger, the title bar changes from blue to green. The light's still on because that's where we stopped with the LED on. But, full debugging experience. Let's put a breakpoint on that red bar there. Now let's press F5 and we'll run to the... Now it went gray, so we're stopped at the breakpoint. I press F5 again. And again, because it was already on. So now so every time I press F5, like now it's going to be off. Now it's going to be on. Now it's going to be off. Now it's going to be on. So you can't really do this even in the Arduino environment without using some kind of debugging hardware or but the regular just out of the box Arduino where you plug a serial port into your microcontroller, you don't have a symbolic debugger like this. And in addition to this, like when we step into something, on the right here we're going to see local variables. This here is the serial console. So it's been 10 minutes since I powered the board up. So or 11 minutes, 676 seconds. And then if I press F5, we go back to the breakpoint again. F9 to switch off the breakpoint. F5, and now it's running without the breakpoint. Control C. So high-level language development experience for your 6502 in the same kind of way we develop for an Arduino rather than a self-hosted development environment. Like having BASIC running up on your 6502 is all very well, but that's self-hosted. And it's a bit limited in terms of this sort of functionality and this sort of debugging experience. And this is kind of where I wanted to go to with, what to do next after you've you exhausted what you're learning out of Ben Eater's board. Right, so that's a bit of the why of it. Another interesting aspect of this, of the why of it, is I'll show you another thing quickly. And you might have actually figured out what I'm going to do from the comments. So let's unplug. I'm going to just pause this and swap machines. All right, what did I mean by pause this and swap machines? Well, let me show you. Take that machine out the way, and we'll put that little device on screen. So what is that? That is basically, it's a... Let me find one quickly. It's a Raspberry Pi Pico device, but made by Waveshare. And why do I like it? Because it has two features that the Raspberry Pi Pico does not have. It has a USB-C connector, and it also has, in addition to the boot button, the boot select button, it's got a reset button as well, which means you don't have to unplug and plug to reset. And with that little micro USB on the RP2040, it's just a matter of time before you destroy your device. Anyway, I highly recommend this version of it, but why am I showing you this? Well, let's just switch boards here. So we were on the Hopper 6502 board. Now we switch to the Pi Pico board because this is a generic Pi Pico. We build the project again. And then we F5 again to launch the debugger. Right? And then we F5 again to run. There you go. It's exactly the same Hopper code with exactly the same development environment, and you can run it on a microcontroller, an RP2040 style microcontroller. And there's a wide variety of boards of RP2040 microcontrollers that you could use. I've got a couple that I recommend. Like this one's a good example. But these are all good too. So these are two from SparkFun, right? They also have USB-C connectors. They also have reset buttons. This is a pretty cute little one from Adafruit. Tiny little board. Also has reset and boot select and USB-C. And this one has I think they all have NeoPixels nowadays. And then this one is particularly interesting. This is a Swedish board. It's called the Challenger. From, what's the manufacturer called? I forget. But anyway, this board here is an RP2040 board with a USB-C. They've got one with a LiPo plug as well, so it's got a LiPo charger on it. And in addition, that thing at the back is the Wi-Fi antenna. So this is an amazing little RP2040 board. But again, why am I talking about RP2040 boards when we're wanting to build a 6502 machine? Well, the reason is the barrier to entry is so much lower. So you might already have an RP2040 board, and if you don't, you can get one locally very quickly. Like I bet you can have one by tomorrow if you wanted one. And that means you can download the Hopper development environment and be up and running, writing Hopper code on the device almost instantaneously. And everything that you learn about the language and the development system is going to apply directly to your experience on the 6502. You're going to be able to take it all with you. So at the cost of one little microcontroller board, it's, I reckon it's a really worthwhile way to learn about the environment before you've even built your board. It's also, I found, like when I've written more complicated programs for the 6502, like I've written a tiny basic implementation in Hopper. I've written a fourth interpreter in Hopper. It was so much easier to develop those on the microcontroller first, and then make them run. And then once you've figured out how it all works, get it running on the 6502 machine. And part of it's just speed. I mean, this is a 8 megahertz clock, but I can overclock the RP2040 to 20 times that speed basically. Okay. Anyway, let's get back to the board and let's talk about, now we've spoken a bit about the how of it, the why of it. And let's now talk a little bit about the what of it, like what is this board? So I'm going to turn that off and just talk about the board in a bit more detail now. Right, so let's talk a little bit about the environment and how to install the development environment and what the point was of the development environment as well. So with many of these platforms, including Arduino, when you're trying to get up and running and you're trying to install, you very often end up with libraries that don't match, third-party dependencies. You need to update the device driver. Oh, look, it no longer compiles. It's it's no longer compatible. All that sort of thing. And it's even worse with things like that run on the whole. I don't want to be disparaging, but if you've tried to install something like any third-party sort of development compilation tool chain, something that requires GCC, GDB, Python, all that, you end up having to install. You usually have some large install script you run that's installing third-party components from multiple sources. They're not necessarily in sync in terms of versioning. There's always something. You always get stuck somewhere in this install script. It's a frustrating experience to try, especially for a beginner, to try and get up and running with one of these platforms. And a lot of these platforms are sort of jack of all trades, master of none, like VS Code, for example. It's designed to do just about anything with just about any language. So to try and get your project up and running on it is nowhere as near as simple as in this Hopper environment. All you do is you say, I want to edit my Blink program, and then you hook it together. There's no make file, there's no build process other than pressing F7 here, and then at the bottom of the screen, you see the build stage going through here. So I wanted to make something that was, to me, the same introductory experience that I experienced as a university student in the 80s when they introduced Turbo Pascal as the way we were going to learn to program computers. Turbo Pascal on, at the time, CP/M machines, and then later MS-DOS machines. It was this one-stop shop. You just put in a disk, you launch Turbo Pascal, and you're programming within seconds, right? So the Hopper development environment is supposed to give you the same experience. You download a zip file, you unzip it, there's an executable in there. You unzip it to a folder, there's an executable in that folder, you run it, you're in Hopper. Done. That's it. And then the other part is if you've got a microcontroller, there's one of these pre-built UF2s. You plug in your microcontroller holding down the boot button, you drag and drop the UF2 onto your microcontroller, you're done. You don't even have to install the Arduino IDE to, or anything else to put the firmware on your microcontroller. Right, so that was part of the point of it, was to try and make it a really easy way to get up and running for the beginner. And yes, and we've got a Discord server as well. So easy to ask questions without being told, oh, you need to read the data sheet, or you need to read the manual, or you're doing it wrong. It's a very constructive environment when you're in amongst people who are all doing what you're doing and supportive of the fact that you're being a success at what you're doing. So that's the point of trying to do this environment. It's a learning environment, and it's supposed to be easy to install and easy to use, right? Anyway, getting back to the board again. As I mentioned, this is my second round of building a board, and part of my objective with the board is, I'm approaching 60, so I have my hands aren't as stable as they used to be, and my vision isn't as great as it used to be. So I wanted all through-hole components. I didn't want it to be finicky. I wanted it to be easy to assemble, which is also helpful if you're not that experienced at soldering or at electronics. So this board is easy to build. I wanted the components to be relatively easy to source. I don't want anything exotic on the board. And that is getting a little more tricky, but I'll do an entire video about sourcing components and about where I believe you should start in terms of ethics as well. For example, Anders Nielsen, who does the 65 Ueno project, has a store online in Denmark where he sells secondhand reused components of all these components. And he takes a lot of the roulette part out of the sort of AliExpress roulette when you try and buy things online and you get fakes and things that don't work and that sort of thing. So he goes through that all for us and weeds out the ones that work, and at a very reasonable prices is selling secondhand chips. And it's, in our consumer society, let's do more secondhand chips when they're available. There's nothing wrong with them. These things run forever, and they're pretty indestructible too. I mean, these things, modern people ship things in anti-static bags, modern stuff. Yeah, good luck destroying one of these with a static from your fingers. It's just not going to happen. Yeah. So maybe the old, Moss ones, but these ones are practically indestructible. So anyway, this project, this playlist on YouTube is going to get you from, first, it's going to show you how to get one of these, how to build one, how to make your own one of these. And if you haven't worked with one of the online PCB fabricators, that's going to be a fun experience in itself, just getting yourself a board, using my design, of course. And then you're going to get from there to here in nice incremental steps where you're going to understand all the bits and pieces. So what's different between my board and Ben's design? So there's also two other names that are really worth giving credit to, and the one is Garth Wilson and the other one is Grant Searle, both of who have spent decades doing this and have published really nice designs for these kinds of boards online. So let's talk about the differences between my board and Ben's board. So the first obvious difference is I'm using a different serial chip. I'm using the Motorola chip, not the Western Design chip. And part of the reason is because the Western Design chip, depending on which version you get, has a bug in it. And you end up needing to put like delays in there to make it work rather than actually using the flags in the in the status register. This chip is rock solid for RS-232 communication. And it's actually simpler to use than the other one. This one's only got two registers in the I/O space instead of 4. It's a very clever design. And I've used it in multiple different boards, and I can highly recommend it. Another thing I've done is I don't use the MAX232 chip and a bunch of capacitors to convert the voltage levels from TTL. So TTL would be 0 to 5 volts. So actual RS-232 is negative and positive like 25 volts or something. So you have to convert the voltages using a MAX32 chip to RS-232 voltages. And, that gets you an actual RS-232 port on your design. And that's the MAX32 there. So you actually plug it in with an RS-232 cable. But all that happens nowadays is that RS-232 cable is not really RS-232. Internally, it's like an FTDI converter that converts it to USB immediately. because you don't have an RS-232 port on your computer. So you're converting it to RS-232, and then you're converting it again to USB. So I reckon we just skip a step and skip some components and just go straight to FTDI. So FTDI is TTL, in other words, 0 to 5 volts, TTL to USB converter without the RS-232 step in the middle. So simpler, less components. And there are multiple devices out there to do this, the FTDI conversion here. So, there's these kinds of devices. And they tend to have a little switch on them, like that switch over there, or this jumper. And that switches between 5 volts and 3.3 volts. So it is kind of important when you get your FTDI cable to make sure that it says, what does it say there? Oh, come on. RS-232 5 volts. Yeah. Because if you got a 3.3 volt one, you'd be a bit disappointed. Anyway, and then on the edge of the board, I've got multiple different pinouts for the different kinds of these devices. There's no standard in how they pin these things out. So that's the first difference, is how I connect it to the to your computer. Still via your COM port, obviously through USB port. But thinking it's a COM port. So first difference between my design and Ben's design is basically a simplification. Second difference is I don't have an LCD on this thing, and I don't have a PS2 keyboard on it, because even though I put those on my first design, I almost never used them after, like proving that they worked and testing them and playing with them. The vast majority of the time, you're going to do everything via the serial port anyway. And in the Hopper environment, there's either the Hopper debug interface, which works via the serial port, or there's just a regular terminal, on the Hopper environment. So let's look at that. So if I plug this guy in again. And now I'm not going to load the debugger. So the program's still there. The program we uploaded is still there, which is some other magic that's not part of the Ben Eater board. But now we can do it. We can type terminal here in our little Hopper console. So this console window here is actually the Hopper environment. And the idea is over time that it'll be the same on all platforms. So it says it found a COM15. Do I want to connect? Yes. And there we go. So there's our debug information coming every time we get a flash. We see how long it's been powered up for, since I just powered it up. So most of the time, you're going to be talking to it through the terminal, and this works both ways. You can type keyboard input in there as well. Turn off the distracting light again. So no keyboard interface and no LCD. I do break out the parallel port interface here, and I give you some extra power pins here. That's so these pins here are ground and 5 volts, and these are the 16 parallel ports pins interfaces, of which some I've already used. So I've obviously got one that's connecting directly to my built-in LED, and then I have this little area here is the I2C interface area. So Anders Nielsen gave me this idea with his 6-pipe Arduino, which was that you could just directly plug one of these little very non-retro OLED displays in there. And then I took it one step further and implemented a serial EEPROM here. And that's what that is. It's I2C serial EEPROM. So these two here, they have pull-up resistors to make I2C work, and they're connected to 2 of these pins here. But if you're not using I2C, you get them for free. So you can just not have this chip on board, and you'll have another 2 I/O ports. But I'm betting you will be using I2C. All right, so that's another difference, the parallel port. What else is different between this and Ben's board? I have a reset button and an NMI button. So the NMI is the non-maskable interrupt button, which is really nice. Even if you implement something like BASIC, it's nice to have a button to do the break. Like if you look on your keyboard that you're sitting at right now, if you're sitting at a computer, the pause button, right of scroll lock, you'll see the word break below it. In the old days, that used to send a control C and break the program you were running in so that you could, debug it. And it's really an advantage to the developer because it means you don't have to poll for the break key in your virtual machine. You can just, wait for an interrupt. And so that's what I do with NMI. So the NMI button here, non-maskable interrupt, is hooked up to a break functionality in the Hopper virtual machine. Reset is obvious, but reset is another place that I differ from Benita. In his design, he doesn't have that great a power-up reset circuitry. And I think it's one of the things I got from Grant Searle's design. It might have been Garth Wilson's design, I can't remember, is to use one of these. So that little chip there is a DS1813, and it's called a supervisor, 5-volt supervisor. And all it does is it holds on power up, it holds the reset line at high, it asserts the reset line, or is it low to assert the reset line, I can't remember, for 150 milliseconds. And that lets all the components on your board have enough time to start up. And it's got to be longer than like 25 clock cycles for the CPU, so that they all come online at the same time, and once they've all had enough time to initialize. So you get a clean restart. So a lot of the time with my experience with the Benita board is that you first had to power up, and then after you've powered up, you'd have to hit the reset button to start again. It wouldn't just do a clean restart. So a clean restart's nice. It's, and talking about power up, there's no power supply on this board, so I don't have an external power supply like Ben did. So I did the arithmetic on, what all these things maximum consumption is, and made sure that it's less than whatever it is, 600 milliamps or something. It's a lot less. And you can always get that out of a USB cable. So the power in the USBs, and it always gets power from your USB port. So you don't have to worry about conflicting, like burning out your, feeding power up the wrong way in either of the circuits, because there is only one circuit for power. It's getting power from your USB port. So that's another difference between my board and the Benita board. I mentioned the serial EEPROM. So the serial EEPROM makes it easy to persist storage. So this little 8-pin chip here is this one's 64K. That's a 64K serial EEPROM here. Yeah, and I've got I can support 128Ks as well. But you're loading what we're doing is we're loading the Hopper, like the Hopper Blink program, for example. I could turn the power on, it'll still be there from when I last uploaded it. You need to store it somewhere. You can't just store it in RAM. It's very difficult to program the same ROM that your firmware's on. So if you give yourself another ROM, serial EEPROM, you can use that as the place to store your programs. So during boot up, Hopper will see if there's a program on the EEPROM, and if there is, it'll copy it into RAM and then run it in RAM. That's how it works. So very handy extra thing to add, and that's all my own. So I mean, I took my starting point for that was looking how Anders Nielsen had done his I2C for his OLED display on his 650 Uinu and his EEPROM programmer, and moving from there, I figured out how to do program these EEPROMs. And again, I was talking about how you debug initially on, a microcontroller. I developed that software on the microcontroller first to figure out the protocol for programming serial EEPROMs. It was way easier to do it on the microcontroller first. And I wrote it in Hopper. So I wrote a driver for these things in Hopper. And then once I had it working in Hopper, I ported to 6502 to the Hopper 6502 assembly language to get it running on this board. Okay, that's enough about I2C. What else is different about this board? Okay, a big difference is I use a CPLD, a programmable logic device, for the glue logic. So on most of these designs, and that includes Grant Searle's, Garth Wilson's, and Ben's, they use a couple of 7.4 series TTL chips to do the glue logic. And what is glue logic? Glue logic is dividing the address bus to say which part of the address bus is your ROM on, which part of your address bus is your RAM on. And because in the 6502 all your I/O is also on the address bus, where is your serial port and where is your parallel port on your device? So you can, and the more granular you want that space to be, the more chips you're going to need. The more logic chips you're going to need to divide the address bus. And again, I highly recommend going and watch Ben's video on breaking down the address bus, because he has a few of them. Like as he adds peripherals, he adds to the logic of his glue logic. However, the problem with those designs is that you've got a hard-coded decision you've made. You're building it into the board where the port's going to be. You can't move them around. Now, you can't see it very easily in this, but if you look at the end of the RAM chip, there's some extra pins I haven't used. See that over there? There's like 4 extra pins. Why is that? Well, in a lot of cases on this board, I've made it so that you can use different chips, multiple different chips. So for the RAM chip, you've got the choice between, where are they? Between this guy here, and this is a very common RAM chip. It's a 32K RAM chip. It's the same one you'll get if you bought Ben's kit. This one here is a 64K chip with a very clever pin layout so that you can just drop it into the same socket. So there's a bigger socket. And if we have a 64K RAM chip, this is a 32K ROM chip, 32K EEPROM. But Hopper is still less than 16K, which means we can make the EEPROM be 16K and make the RAM be 48K, which is quite nice. And the way we'll do that is just by reprogramming the glue logic chip to tell it where things are. And another thing is, I made a sort of a controversial decision, controversial in terms of the people I've discussed it with, in terms of putting my ports, this port and this port, I put them in the 0 page, in the 65020 page, for various reasons, which I've got an article on my Hackster where I discuss the merits of my decision. I mean, I did it for good reason. But if you're trying to run some legacy software on my board, like you're trying to run BASIC on my board, Microsoft BASIC, that's not going to work, because it's going to have the serial and parallel interfaces mapped to somewhere else, and definitely not in the 0 page, because it's probably using the 0 page for something else. So I wanted to make it possible to reuse my board for other things, not just Hopper. And you could use this, you can, again, reprogram the CPLD to put them in a different place in memory. Anywhere you like, really. And this is a 8-cell, 8-cell GEL chip. But again, I made the design. I looked for pin compatible options, and you can also use a 10-cell version. So you can either use the ATF22V10 or you could use the GEL20V8. They have the same pins, only the one on the left has more cells, which means you could do more granular address breakdown. And while we're looking at it, I've got footprints here for different crystals, different crystal can oscillators. So either the DIP 8 ones or the DIP 14 ones. So you can have the big ones or the little ones. And there's some choices you're going to make when you build your board, like which components you're going to put in sockets and which you're going to solder directly onto the board. And instead of having like a divider to share the same crystal clock between the CPU and the serial port, I just chose to have two cans. But you can run this board on one can, and that's what this jumper here is for. Single clock. It says one clock. So if you put one clock in here, it'll run the CPU off this clock. And you can, so that's, what's that one? 3.8684, 3.6864 megahertz. And so these cans have pretty peculiar frequencies because they've got to match baud rates for RS-232. Whereas this, I wanted to have the advantage of having a simple design where you can change your clock speed here just by changing this crystal. So you can just pop it out and pop in a faster one, and you'll double your RS-232 speed. But you can do that from software a bit as well, but it's a bit limited. And then in this one, you can put in a 1 megahertz clock if you're, debugging. If you want it to run slower, like you're trying to, see things on your oscilloscope or whatever it is, or just put an 8 megahertz clock in to clock it to the max. And I've tried. The 6502 can run faster than 8 megahertz. You can overclock it. You can certainly run just 10 megahertz. But you run into limitations with the speed of, I think that the first thing to be a limitation is the EEPROM. So without cleverness, there's not much point running faster than 8 megahertz. You'll just make your life a misery. All right. So I think that's all about the difference between my board and Ben's board and some of the motivations of why I did it this way. So let's just recap. What am I going to do in the rest of the series? I'm going to start with the next video is going to explain to you how to get your PCB made. In the description for this video, I'm going to give you a link to Ben's page. Because I do highly recommend you, if you haven't been through his process, it's worth getting his board. And if you do, you'll get that chip, that chip, that chip, and that chip. So all 4 of those. You'll get the RAM chip, the ROM chip, the CPU, and he uses the same parallel port as I do. I use the same parallel port he does, other way around. You might even I think you get a crystal oscillator as well. So yeah, you buy his kit, you get a fair amount of these components, and I'm going to assume you've got an EEPROM programmer as well, and like I say, he sells those. And then in the next video, I'll talk about how to order your board, and I'll start to talk about the bill of materials of the components that you're going to need to get. I'm also going to talk about tools that I recommend. I assume the obvious, like that you've got a soldering iron, but I'll talk about other tools that I find useful that I recommend. And that includes things like these cables, the FTDI cables. And I've been through a couple of different variations, so I've got some thoughts on that. After that, I'm going to walk through my recommendations for how you source these components. And you don't need to get anything at all from Ben. I mean, you don't need his machine. You can just jump straight to this one. And Jameco used to sell Ben's kits. I don't know if they still do, but they sell most of these components as well. So you could buy directly from them, including the EEPROM programmer. And then we're going to start the assembly, and we're going to assemble it incrementally, testing bits as we go. It's the easiest way to bring one of these boards up. Even though you've got a proven design here, it's still worth not just, if you do the whole thing and plug it in and it doesn't work, what are you going to do? How are you going to find the mistake? Whereas if you build it in incremental steps, it's much easier to figure out where things go wrong. All right. We'll leave it at that. And I look forward to your comments and feedback, and especially questions if you think I missed something important that you don't understand why I'm building this the way I am. Oh yeah, there's another thing. One more thing. I highly recommend, I left the space around this. I left the space around the EEPROM and put it in this corner of the board so that you can put a ZIF socket in, and it'll work with this low profile ZIF socket like that one, but it'll also work with the regular ZIF socket like that one. It fits on the board because you're going to be pulling that chip out and putting it in quite often. So it's worth having a ZIF socket there rather than just a regular socket. All right. Thank you for watching, and enjoy the rest of the series.